discussion of the physiology of the retinal circuitry, and what leads to our output for this lecture will be ganglion cell firing. All right? So, in my mind, physiology is closely related to engineering, so you have to sort of think of it that way as well. And the question then is, if you're an engineer, like, what's the purpose of the eye? I mean, what's the eye supposed to do after all? And it transmits visual information derived from the external environment. And that information that it's transmitting ultimately is based on just three properties of light, and that is transmission, reflection, and absorption. If you're a photographer, you realize very quickly about the importance of light and what you're doing when you do photography. It's really about reflection and absorption. And then the question, though, is that's what's coming in. That's your physical start point. But that's not what the eye wants to send to the brain. What the eye wants to send to the brain is information about ambient lighting, of edge detection, of luminance and color of the objects that you are looking at, okay, and the movement of those objects. So the question is, how does the eye accomplish that? And that's physiology. The problem from an engineering perspective is that ganglion cells fire anywhere from 0 to 300 hertz, which is an amazingly wide range when you get down to it. I mean, that's incredible for a neuron to be firing up to 300 times a second, or as low as 0. The problem, and you say, well, that's pretty good. No, it isn't, because the luminance in our environment, okay, varies by 14 orders of magnitude. 14 orders of magnitude, okay? So 300 hertz is not going to do it, all right? You're not going to be able to see in all lightings with that kind of constraint. So then that becomes the question is, how do we adjust to be able to see objects? Everything from wake up in the middle of the night and you're in a dark room, all the way to snow on top of the mountain and veil in the middle of, and bright sunny day, and still see it all. And so, of course, we constrict our pupil. That's one of the first things that we do, is just let less light in. But that's not, in the end, nowhere near enough when you're dealing with 14 orders of magnitude. And so you have to have adaptation of the retinal sensitivity to ambient lighting is ultimately what we're heading to in this lecture. This is the target, is how do you do this as ambient lighting changes and maintain vision? Now, that's really the engineering question. And the answer is you're going to alter the sensitivity of the photoreceptor, and you're going to use the retinal circuitry, the retinal neuronal circuitry, to solve this problem. And then, of course, central processing will help a little bit. But if you just send a bunch of white to the brain, it can't tell what's going on. It needs the information. So I'm not going to, we had a whole long hour last year on this, and I'm not going to repeat that, but this picture is just to sort of show you all the parts that we're dealing with in the eye, everything from the cornea, the aqueous lens. You understand the roles of refraction, and I know in your clinical talks you deal with this a lot, and so I'm not going to. And we're going to focus our question at the level of the retina, is where we're really going to be dealing. And this is just to remember that all the light that's coming through is coming through this whole vascular layer as well. And to remember that you have all of these principles of reversal of the image on the retina and those sorts of things. All those things are true, and we are not going to deal with any of them today. So let's take a look at the retina and start with development. The retina is an interesting structure because we always say the eye is part of the central nervous system, and the retina is part of the central nervous system. That's true. And yet there's something very odd about it, because the retina also has a pigmented epithelium, which is part of it, which is hard to think of another example in the central nervous system where you have pigmented epithelium. The answer is you don't. Okay, so this is, it's central nervous system which is developing under the influence of the prochordal plate, okay, which is notochordal, which is somewhere between mesenchymal and epithelial. So all of that is happening. At any rate, these are your pictures. Here you are at a 4 millimeter embryo, and this is going to become the optic vesicle, it's going to be known as, and then that's going to invaginate, and as it does so, part of it, okay, actually develops to become the lens, but what was the real wall of the vesicle becomes retina and pigmented epithelium. Right? And then that separates and develops. And so I have another picture just pointing out the lens placode, which is developing in this little embryo. And I like this picture always because it really shows you the invagination. There are 5 families of cells in the retina, and I'm definitely calling them families of cells. You have the photoreceptors, and you know that they're both rods and cones, and we're going to deal with them separately. And then you have this group called horizontal cells. You have bipolar cells, amacrine cells, and ganglion cells. And these 5 are just families because you have just, in some cases, and maybe amacrine, there may be 200 different amacrine cell groups in the retina. Now, one of the things that I don't even know if I have a slide on it, but let's just remember that the only action potentials that is going to appear in the retina is going to be in the ganglion cell as it's leaving. Everything else, all of the photoreceptor, contact, bipolar, amacrine, horizontal, none of these cells are capable of firing action potentials. All of them are going to be graded according to stimulation of light. All right? So there'll be no action potential summation. All that kind of stuff is out the window. These are very different kinds of systems that we're going to be looking at. Now here's the pigmented epithelium. So light is coming in through the pupil would be down around the 2nd floor on this picture. Okay, so in comes the light. You all understand that the whole system is inverted in an odd way. You would think that your photoreceptor would be on the surface of the retina, where it would experience the light first. You don't want light going through all of these elements, okay, before it gets to the photoreceptor, and yet there are reasons that that's true, and we'll discuss those reasons in a little bit. At any rate, your photoreceptors are in fact adjacent. They are in the most outer portion of the retina, adjacent to the pigmented epithelium for a reason. And then these are called the outer segments of the photoreceptors. Then you have the nuclei of the outer receptors and their synaptic region. And these are synapses, even though they're not firing action potentials. These are still bona fide synapses. The photoreceptor cell will either synapse on the bipolar cell or the horizontal cell, and we'll look at this in a lot of detail. And then the bipolar cell will transmit its information to ganglion cell and amacrine cell. And then it leaves. And once the ganglion cell will summate all of this information and decide whether it's worth an action potential, which can then be transmitted all the way to the lateral geniculate, in most cases. And this is from the anatomy lecture, and just to show you, here's the choroid and the pigmented epithelium. Here are your outer segments. Here's your nuclear layer. This is the inner, the plexiform layer, the outer nuclear layer, the outer plexiform layer, outer nuclear. So here's your photoreceptors. Here's the outer nuclear layer. Here's their plexiform layer where they're contacting the bipolar cells. Here's the inner nuclear layer, which are your bipolar cells. The inner plexiform layer, which is all of this for amacrine, bipolar to ganglion, and ganglion cell out. The actual act of phototransduction occurs in rods and cones, of course. They are the photoreceptors. And their job is to convert the energy of a photon, a single photon, into a change in membrane potential that can be processed by the retina, eventually to generate the action potentials in the ganglion cells. Okay? So the energy comes in as a photon. It is absorbed by the rods and cones, and the rest of the retina, including all of the other synapses that we just talked about, are going to amplify, compare, make use of, and get the ganglion cell to fire in such a way that luminance and objects and color are being transmitted to the central nervous system. Both rods and cones conduct the phototransduction act, but they do it in, there are major differences between them that we'll talk about. They both have the outer segment of membranous discs which contain the photopigment. They both have inner segments which contain their nuclei, and then the synapses onto horizontal and bipolar cells. And so here they are. And these are just the anatomic differences. The rod is longer and more uniform, has far more discs than the outer segment, which would make you think that this is going to be the more sensitive, but it's not. The cone is actually much more sensitive, as we'll talk about. And this is EM. I always like to translate cartoons into reality every once in a while, and this is what the real disc, the membrane set looks like in the outer segment. Notice this little stalk. We're not doing anatomy today. Why are the photoreceptors put adjacent to the pigmented epithelium? Pigmented epithelium is absolutely essential. First of all, it brings the blood supply to the retina, right, through the choroid. All right. Secondly, the pigment prevents light scattering. It will absorb anything that makes it that far is going to get absorbed by the pigment. And then it has two much more important functions, which are fully integrated into this recycling process of vision. So you're going to see that when you absorb a light, it creates an irreversible chemical reaction. And that irreversible reaction has to be addressed, and it's addressed by the pigmented epithelium. And I'll show you that in a minute. So here you go. This is the vitreous humor, right? Here's your retina. Okay, photo segments, right? The photoreceptors, and there's the choroid, filled with pigmented epithelium and blood vessels. And then the next layer is the heart supporting sclera. So here you are, and this is actually, they're quite interdigitated. Your pigmented epithelium and the photoreceptors are abundant. I mean, it looks like a tropical rainforest to me. These processes really go down and surround the photoreceptors. So here's recycling act number one. These discs that contain the rhodopsin and the other retinal opsin molecules, they are constantly wearing out, and so they have to be replenished, all right? And so what happens is they're made close to the nucleus, so that's going to be at the bottom of the photoreceptor, right at the stalk here, and the new one, so if you give a dose of tritium, let's say, and radiolabel, what you see is that the tritium appears initially in the part of the photoreceptor that's closest to the nucleus, and then it gradually migrates its way up to the top. When it hits the top, it's then phagocytosed. In fact, there. Here's a piece of disc actually being phagocytosed up here. Okay. All right. And then it's shed, and the portions are taken out and reused and passed right back down again. So it's an efficient way of dealing with it. So that's recycling act number one. We'll come to recycling act number two when we talk about the actual retinal interaction with the photon. Y'all with me? All right.
Why do they want to recycle?
Well, why do we recycle paper?
So it can be used again.
You have less waste and less energy to get back to what you wanted, as both answers. You don't have to transport the waste away. I mean, everybody wants to get to zero recycling, no more landfills, and that's true. If you want to recycle, those things are going to have to be sent generally some distance away, whereas you'd much rather have a local recycling. It's more efficient. It's energy efficient is the answer.
The previous slide. Is that why you get like vision affected in Melas? Like,
say it again. Is vision?
Is that why you get the vision affected in Melas because of this system, like the mitochondrial involvement?
I honestly don't know. So I'm not sure. All right, phototransduction. All right, this is inside out, upside down. There's something backwards about this, but that's the way it is. So rods and cones are maximally depolarized in the dark, and their resting membrane potential is at -40. You know, a neuron's resting membrane potential might be -70, right? Hyperpolarized might be -80. So you start to fire an action potential in a neuron, not the photoreceptor, but in a neuron, maybe around -30, something like that. The photoreceptors live in a depolarized state in the dark. While you're sleeping, when your eyes are closed, when you're sitting in the dark, your photoreceptors are maximally depolarized. Okay? Absorption of a photon in the outer segment hyperpolarizes the cell. So It's the opposite of what you would expect. It doesn't excite the photoreceptor, it suppresses the photoreceptor. That's the way it works. The degree of depolarization, right, reflects the intensity of the light flash, which is a function of the number of photons. But I want to be real clear about this. The eye does not detect the absolute number of photons, which varies over 14 orders of magnitude in our environment. So it can't do that. All right, we'll come back to that. Yet the response of the photoreceptor is in this way to a receipt of a photon. And you say, well, you know, it doesn't matter if a signal drives it up or down, drives it darker or lighter, as long as the neurotransmitter release of the photoreceptor is related to light intensity. Up or down, you don't care. As long as it's related, more is one direction or more is the other direction, it doesn't really matter. So here's a light flash, and what we're doing is, I like your book chapter a lot, by the way. This lecture really comes from the book. I like the book a lot. I've varied it, but it's fundamentally the book chapter, and most of the figures are from the book from now on. And so here's your light flash. And then if it's a very weak light flash, so you get a very minimal change in the hyperpolarization. See, we're going from -40 down to -65 with a light flash. All right? Maximal stimulation, and you get down to about -65 or just below. Okay? So that's what's going to be happening, okay, as a function of the amount of light that comes in. Now, glutamate is the neurotransmitter of both rods and cones. So remember, it has a synapse onto the bipolar cell and onto the horizontal cell. That synapse is glutamatergic. The neurotransmitter release, this is going to be very straightforward. This does fit intuitively. The neurotransmitter release varies directly with calcium influx and indirectly with potassium efflux. This will this will depolarize your cell, and sodium comes in with it. That will depolarize the cell. This will hyperpolarize the cell, just like in a neuron. So during depolarization in the dark, the calcium influx is very high. During hyperpolarization in light, the calcium influx falls. This is the mechanism by which this inverse relationship occurs. Calcium influx occurs through a voltage-gated calcium channel. Hello. All right, that is regulated by cyclic GMP. So this is a cyclic nucleotide regulated calcium, voltage-gated calcium channel. Potassium efflux is a constant. It's sometimes referred to in physiology as constitutive. It doesn't change with circumstances. It just is always running. Therefore, you control the system by controlling calcium. Since this is always running, if you shut this off, the cell will hyperpolarize. When this comes in, the cell depolarizes, and that's that. The potassium just is sort of always going. So you accomplish this then, not surprisingly, since this is a cyclic GMP-dependent voltage-gated calcium channel, that if you want to shut the channel, get rid of the cyclic GMP. And that's the way it works. That's why I said this part's intuitive. So photon absorption results in reduced cyclic GMP. We'll talk about how in the next slide, but it doesn't matter. Following this logical chain, and reduced cyclic GMP closes the voltage-gated calcium channel, which leaves the potassium channel open, and so the cell hyperpolarizes. And when you hyperpolarize, you release less neurotransmitter. And all of this follows the usual logic. The only part of this that seems upside down is that the stimulus of light results in hyperpolarization. But the mechanisms by which this occur are totally intuitive to us. There's nothing new to learn in here, really. So, summary slide in the dark, okay, here you are, you're depolarized, right? You depolarize the cell, and you have all this calcium flowing in, and then you bring the cell into light, and you're going to get rid of, so here you are, you're still in the dark, the calcium and the sodium are coming in, the cyclic GMP is bound, the channel is open, the potassium's running, you shine light on the system, it hyperpolarizes by shutting the calcium channel and leaving the potassium channel open. So that's what we just said.
So how does photon reduce cyclic GMP?
I'm glad you asked.
Oh.
So, okay, that's exactly right. So how does the remember what we have a photoreceptor. We have to, in order to know that the photon has come in, we have to absorb it. It has to result, the presence of the photon has to result in a biochemical change. And the biochemistry has to be such that the absorbing molecule is in the right energy range for the photons that we see. So the system is very simple. You always use retinal to absorb the photon. You control the energy level at which the retinal is sensitive, the wavelength of light if you prefer. You control that by embedding the retinal in an opsin molecule. Okay? Which opsin molecule determines whether it's a rod, okay, or whether it's part of color vision and which part of the spectrum it's seeing in color vision. So that's the opsin that determines that. And the opsin determines that by torquing the molecular bonds in the retinal so that they will absorb a particular frequency of light, preferentially. Okay? So everything, this is good physiology. This is real physiology, all right? So the retinal always absorbs a photon. There's no variation in that. And retinal is an aldehyde of vitamin A, so eat carrots. Retinal is bound to one of numerous opsins, okay? But in all cases, the absorption of the photon, in all cases, absorption of a photon converts 11-cis retinal to all-trans retinal. And when that happens, the opsin gets screwed, okay? So the opsin may control the stretch of the bonds on the retinal while it's sitting there, but when you convert from 11-cis to all-trans, okay, everything changes, and the opsin just lets go. It doesn't know what to do with itself, and you activate the opsin. Well, once you activate the opsin, which is a transmembrane protein, I'm glad we did that lecture a long time ago, and you have this 7 transmembrane domain, and we talked about this. So here you are. Here's the retinal sitting in the opsin. Here's your 11-cis retinal. This thing's spinning around and can be controlled by the opsin. But then you make it all trans, and the opsin can't deal with it anymore. It has to let go and change its own configuration. And now to get to Annie's question, so what? So then the absorption of light by the retinal and the resulting change in the opsin phosphorylates. You activate the opsin, if you will, is a phosphorylating protein, okay? So it's a kinase, if you will. So opsin is a form of kinase, and it phosphorylates transducin, which is sitting right next to it. The transducin activates a phosphodiesterase, and there you have it. Now, once you do the phosphodiesterase, you destroy the cyclic GMP. You destroy the cyclic GMP, you close the calcium channel, you hyperpolarize the cell. You release less neurotransmitter. So the final output of the absorption of light is less transmission out of the photoreceptor. Okay? Summary slide. Light, rhodopsin, transducin, phosphorylate, phosphodiesterase, destroyed cyclic GMP, close the channel. The potassium channel's still open, and that's it. You got a hyperpolarized cell.
Why they call rhodopsin here? Why they call rhodopsin?
Why do they call it rhodopsin?
I know rhodopsin.
It was
is
historically,
famous,
it was relatively red. The road comes from red. It's just a historical, because there was.
But it is the opsin that you're talking about.
Rhodopsin is the combination of retinal, 11-cis retinal, with the opsin, which happens to be in the human rod. So it's a particular opsin that is in the rod. All rods have the same rhodopsin. Cones vary in which opsin that they have. Okay, but all of the rods always use rhodopsin. And that's just a historical name. It was the first one found. The term opsin was broken off of the rhodopsin once they realized that there was more than one. Now, amplification of the signal. Remember, we're doing physiology. The single photon comes in. A single rhodopsin activation activates 800 transducin molecules. That's 3 orders of magnitude. Okay? Each transducin molecule can only activate one phosphodiesterase, interestingly, but then each phosphodiesterase, on average, catalyzes 6 cyclic GMPs, so you have a 2,400-fold increase. The net result is that each photon coming in, okay, and absorbed in the photoreceptor, okay, results in closure of 200 ion channels and a hyperpolarization of 1 millivolt. And now, this is the only slide I have on this. The second reason that the receptors are embedded in the pigmented epithelium is that it's the pigmented epithelium that has the enzyme machinery to regenerate 11-cis retinal. Okay? So you have a lot of separation. The nervous system utilizes a lot of far more enzymes than any other organ in the body. Okay? And yet there are certain things it doesn't want to do. Okay, and it farms those things out to neighboring tissues, whether it's neurons giving it to glial cells or glial cells giving it to endothelial cells or that sort of thing. And this is just one of those examples where the retina doesn't want to deal with this problem, and so for whatever reason it was more advantageous to give it over to the pigmented epithelium. That's a sort of teleistic argument. The photoreceptors then, okay, adapt to ambient lighting. So that, remember, we close the pupil, we adapt the photoreceptor. This is still going to be a relatively small part of it. But the adaptation is sort of just in its own, it has its own feedback loop. And that is, if you close the calcium channel and you depolarize the cell, all right, then what happens is that you inhibit guanylate cyclase and rhodopsin kinase. Remember I said it's really a kinase. All right, so that they are now inhibited and the system rebuilds and the cell depolarizes itself again back toward -40 and it's ready to fire again. Okay? All right, so you follow all this? We're all together. All right, good.
I don't know about this last one. So why is this high
Well, you want to
level?
end the signal, right?
So even though you consistent have the light exposure, they still
Right, so
have
say
the-
you saturate, always think
Okay.
about saturating. If you
Mhm.
saturate the system, you shut the system down. Okay? And that's the answer. And of course you have genetics as well, and the nucleus is not that far away, so if the cell is living in if it's in Africa or the south of France as opposed to Norway in the winter, so you want different levels of all of this stuff.
So, but
I mean, Norway doesn't get as bright as the south of Provence does.
The trigger of the recovery is starting from the calcium channel.
Say again?
The trigger of the reset.
Right,
is
the light
triggered from
itself,
calcium.
the point here is that the light itself and the constant exposure to light,
Can open
and
it.
especially at saturation, provides a feedback mechanism to downregulate and let the system replenish itself. But you can make it less sensitive. You can do long-term inhibition. You can synthesize more guanylate cyclase if you want, right? Okay, or less phosphodiesterase if you want. Okay, rods and cones differ, so let's just focus on the difference between rods and cones. First of all, they have totally different functions, all right? Rods are all about the dark. Seeing in the dark is what you want to do with your rods, and seeing in bright light, fine detail, is what you want from your cones. You want to be able to read, you want to be able to pick the caraway seeds out from the pepper, that sort of thing, okay? So you like a lot of detail, that's where you use your cones. At night, all you want to do is not fall off the road, so you just use your rods. They have a different sensitivity, and this is in the opposite direction of what you would expect. Right now, we are talking about the photoreceptor. We are not talking about rods or the retina as a system yet. We haven't gotten to the retina. We're still looking at cellular elements. So the rod is actually much less sensitive than the cone. The cone is 100 times more sensitive to photon than the rod is. I don't know why. Also, rods saturate quickly, and cones do not. And also, the cones will recover faster. So they are capable of conveying much more information. The amount of information being conveyed by a rod is relatively limited. They have different distributions, rod and cones in the retina, and they have different connections and different degrees of convergence. So here you are, okay? So here's the electrical, the inward current in a rod, all right, it's fast onset and sustained. Here you are in a cone, it's not at all sustained, it's extremely short, okay, with a reversal as well. You have convergence of 15 to 30 rods onto a single bipolar cell in a way that it's going to be very interesting when you see this. Whereas a single cone may synapse onto a single bipolar cell, which may synapse onto a single ganglion cell. They may go 1 to 1 to 1, just like that. Rods don't do that. Rod's sensitivity comes from the fact that this whole section, you're going to have a big section of retina functioning as a unit. And I'll show you how that happens in a little bit. Very, very interesting. Now, we talked about the problem of having all of the cellular elements, okay, in the way of the photon getting to the photoreceptor. But actually, the way that we have solved that problem is through the foveola. That is, where we want the fine detail of a single photon being caught and transmitted faithfully to the ganglion cell, we clear the deck. All those elements of the inner layers of the retina are removed from, as well as blood vessels, are removed from the area of the foveola. So that's actually the solution, is to get rid of it for a limited area where you are most interested. Of course, that's also where you want to concentrate your cones. Right? No point in putting them out so where are the cones? The cones need to be in here, in the fovea region and in the foveola in particular, all right? So you don't want them spread out all over the retina where they can't do any good. On the other hand, the rods, which don't need to be in here at all, they don't serve that purpose, they can be spread out all over the place in order to bring in low levels of light and see dimly objects that you can then choose to focus on if you want to. Now, color vision, just focusing on, of course, we're going to be talking about cones for a minute here. Rods don't have color vision. So the opsons of the cones are what confer, as we said before, the different sensitivity by torquing the 11 cis-retinal molecule. And as a result, they change the wavelength at which energy is absorbed. You have large membrane depolarizations of a cone. So here's the problem. All right, this is not clear. How does the retina detect a color? So, here, like I said, I haven't given this lecture before. This is your spectrum of wavelengths that opsons are capable of generating. So here are your rods. All right, here's a short wavelength. That's a high energy. All right, here's a medium wavelength and medium energy. Here's a long wavelength and low energy being at the red end of the spectrum. Okay, so you would think, well, if this ganglion cell is firing, then it must be long wavelength. Not so. Okay, not so, because this guy is going to be firing as well. And even if this is more sensitive than this, it's not that much more sensitive. And if I put 2 photons in this one, it's going to look just like this one. So that won't work. So actually, and nobody really fully understands this, but it is recognized that color vision depends on this mosaic pattern. And what the retina actually does, and probably assisted by the brain, is to bring in this information of, well, these types of ganglion cells are firing at 60, and these types of ganglion cells are only firing at 45, and these types of ganglion cells are not firing at all. And so it's going to make a comparison among the 3 different color ganglions, and that's where color comes from, okay? Not from the individual ganglion cell. And basically, that's what this slide is saying, okay? If you have all this sophisticated stuff at the level of the photoreceptor, what do you need all the circuitry for? And well, we haven't gotten to edges, we haven't gotten to movement, and we have not dealt with the problem of 14 orders of magnitude of ambient lighting. So that's what the circuitry is for. All right? So we move to the on-center, off-surround concept. Now, I'm assuming that you have this concept. I'm going to go over it with you. But you have a sense, you know that there are on-center, off-surround, and off-center, on-center, you know, it's like, but that's not what I want to deal with. So I'm going to assume that you know that. And the question is a little bit of detail of how it works at a different level than usual. And also, how do we use this on-center, off-surround? And you're going to be, it is, the funny thing is that this is the, not only the solution for edge detection, which is what you think of, okay, but this is also the solution to the luminance problem. So this on-center, off-surround becomes used in a much more general way than I had ever thought about before studying this chapter, okay? So the thing is, I've said before, the retina is not a photomultiplier tube. So a photomultiplier tube counts the number of photons, okay? It doesn't do that, okay? And it won't give you any answer about how many photons were coming in, okay? You can't tell because it's adjusting itself for luminance all the time. So what actually is vision is luminance contrast. That's what really matters. The book is, get this, the book, the chapter in the book made this statement, and it was like, oh my God, when it said that. So it said, pick up, when you're looking at this page, hand me that, okay? When you're looking at this page, just listen to this. This is what it says. There's more light reflecting off the black letters in bright sunlight than there is reflecting off the white page indoors. Let me just say that again. There's more light reflecting off the black letters in bright sunlight than there is light reflecting off the white page indoors. But it appears black. That's what's funny, is it appears black to us, even though the amount of light may be 3 times more. Okay? So it's not luminance, it's luminance contrast is what we see. And I don't know a better way to say it than that example. It was like, that was mind-boggling to me. It was like, oh my God. All right? So everything that we're seeing is adjusted for background luminance. That's the key. All right? And it's done via the on-off center surround. All right. This is the information which is encoded in the optic nerve. This is actually from the anatomy lecture. Luminance, edge, movement, detail of spatial contrast, and color. I got that right without knowing it. And so the question is, how do you convert all this information? Ganglion cells are specialized. You should not think that all ganglion cells are the same, or that they derive their properties from their connections in the central nervous system. That is not true. They're conveying different information. In fact, you have two, all of them, of course, are going back to lateral geniculate, right? That's the way station. Rarely, some of them will go to suprachiasmatic, some of them will go to superior colliculus, but the vast majority go to lateral geniculate, and then on to V1. The M-type are called magnocellular ganglion cells. They respond transiently even to sustained illumination, and they respond to large objects, and so they're sort of gross. And then there's the P-type, parvocellular, which are more numerous, which have small receptive fields, which are quick on and off, which respond selectively to specific wavelengths. And these are well suited for analyzing detail of form and color. So even as they leave the retina, before they're connected to the central nervous system, they already are carrying specific information. Now, the internal circuitry, right, gets really messy because rods and cones can both influence the same ganglion cell, but they get their information, even when they're going to the same ganglion cell, they go by a very different way. Rods do not directly access ganglion cells. And the bipolar cells from rods do not access ganglion cells. So that's why they're so different. Rods synapse on rod bipolar cells, like my high school principal, grammar school principal used to say, boys play with boys and girls play with girls, okay? It's like no mixing, okay? Rods will synapse on rod bipolar cells, cones will synapse on cone bipolar cells, okay? The rod bipolar cells do not contact the ganglion cell. Rod bipolar cells do not access the ganglion cell directly. They activate amacrine cells, and the amacrine cells contact the ganglion cell. I am not going to talk a lot about amacrine cells. We're not going to be able to get to that topic. Maybe a grand rounds one day. The convergence of the rods onto bipolar and onto amacrine, okay, so convergence, and then it's designed, as you know, for sensitivity to light. The system now, even though the photoreceptor was not the most sensitive portion, when you put the system together, its purpose, because it covers large areas, because there's a lot of convergence, you develop the sensitivity. It's not around the photoreceptor. Cones, you got this simple one cone, one bipolar, one ganglion cell, nice and simple, very designed for high acuity, but less sensitivity overall as a system. Now we have to get to the center surround. Wow. So an on-center ganglion cell, wow, meaning what time it is. On-center ganglion cells, fire a burst of discharges when the light strikes the center. That's what makes them, that's a definition. Okay, so on-center means that the discharge rate of the ganglion cell goes up when the center of its receptive field is illuminated. That's an on-center. An off-center ganglion cell increases the discharge rate. It doesn't go silent. It increases its firing rate when the center falls dark. In both cases...
What is the difference of a burst of discharge versus an increase in discharge?
Well, burst implies a non-steady firing rate.
Okay.
In both cases, an inhibitory surround antagonizes the center of the receptive field. So if the center is on, then the surround is off. If the center is off, then the surround is on. And that is going to drive the system toward an intermediate level of firing in uniform lighting. So that's the key now, all right? When you get to uniform lighting, you're going to activate both the on-center and the off-surround, or off-center and on-surround, it doesn't matter. But you're going to do them both. And so you're just going to drive the system to an intermediate level because the surround gets to influence the center, and vice versa, for that matter. So you only get luminance contrast when you selectively activate the center, okay? That's the basis of it. And that is also the basis of this ambient lighting luminance adjustment. It's the same issue. Now let's look at this. This is a nice diagram. So you have to pay attention here. This is time, not space or a different receptive field. This is the same receptive field in time. It's an on-center, off-surround. Well, so this is the receptive field, and they're saying if this was an on-center, this is how it would behave. If this was an off-center, this is how it would behave. And it's as a function of time. So these are the times, T0, T1, T2, T0, T1, T2. All right? So the system is uniformly dark. All right? You have almost no discharges in the on-center, and you don't have many discharges in the off-center either. Why not? Well, because the on-surround is also not illuminated. So it moves to this sort of blah, sitting there. Now, shine the light on the system, and this gets a burst followed by a sustained level of higher activity in the on-center. And the off-center, if this was an off-center ganglion cell to this receptive field, it would shut down. Okay? Turn the lights off again, and first of all, the off-center now fires a burst that the lights went off. Okay? And this simply stops firing. Which gets to the point of why have on-center and off-center? Why not just go with an on-center? We'll talk about that in a minute. At any rate, here you are, T0, T1, T2, and what we're doing is we're taking this low level of ambient lighting and we're putting a shadow in, so it gets even darker, all right? The on-center shuts down, the off-center starts with a burst, okay? Remove the darkness, return it to ambient lighting, okay? And you get a burst from the on-center, and this guy falls quiet. So you signal on, you signal on, you signal off. You signal off, you signal on. Pretty cool. You can't do that if you only have a single cell type. All right? So your signaling is much more discrete this way. Now, here's a situation where you go from dim light to what we've talked about before, but then expand the light and let it go into the surround, and you see what happens. It goes to an intermediate level, then turn off the lights, and you get a little bit of a burst in the off center. All righty? This is the same. On and off ganglion cells are distributed roughly equally. You have roughly equal number, and they're distributed roughly equally throughout the retina. All right? This is not like rods and cones, okay? Why have them both? You just saw the answer to that. You can now signal on and off. The other reason is that if you move, so the retina adapts, right? That's what we're going to be talking about in a minute. We're going to talk about luminance adaptation. So if you adapt to an intermediate level and you only have one cell type, so it's on. Let's assume it's on. It could be off, it doesn't matter. You turn the light on, it starts firing faster, right? Then it adapts, and you have a lower firing rate. Now, turn the system on again, it can go up. But turn the system off, you don't get a signal, right? Because it had adapted, so it wasn't firing anyway. So you can't signal a diminution in light if you only have one, or the other way around. You can turn the system upside down. You have to have an on system and an off system in order to be able to see both increases and decreases of light in an environment in which the retina is constantly adapting to its ambient luminance. And that's the answer. What do the bipolar cells do? So this goes on. This lecture is not, we're not going to be done at 1 o'clock, I'll tell you that. Ganglion cells are contacted, ganglion cells now, the output cell is contacted on ganglion cell, on bipolar cell. Off ganglion cell, off bipolar cell. All right? They're actually in different plexiform layers. The photoreceptors can directly contact both the on and off bipolar cells. Bipolar cells do not fire action potentials. Nobody does. They use a graded membrane potential like everyone else in the retina. All bipolar cells release glutamate. All photoreceptors release glutamate. All bipolar cells release glutamate. The selective process response on or off to light is determined, is due to the different glutamate receptors at the level that the photoreceptor contacts the bipolar cell. So the question is, do we want to stop? This has, first of all, been a lot of information, and talk about saturating and ambient adaptation. So I'm perfectly happy with that. I don't know when we can continue it, but because we still have, yeah, we've covered, most of the slides are done, but the information is still sort of coming. And a slide like this is going to take us several minutes to go over. So what do you want to do? Does everyone need to leave? Probably we all, pretty much everyone, 1 o'clock, or no? You want me to continue? I'll continue. I know. What do we want to do?
Do we have space? I'm the consult attending.
I'm the consult attending, so I mean, to me, I'll be done in 10 minutes. I mean, this isn't going to run on forever. Keep going? All right, so we're going to keep going. Hoping this doesn't put me to the beginning again. Good. All right. So we're down here. The selective response is determined by the synapse of the photoreceptor onto the bipolar cell, right here. So, all right, on bipolar cells, all right, so glutamate is released by the cone or rod. It's always glutamate. So the question is, how does the bipolar cell receive it? What is the glutamate receptor that it uses? All right, remember here that light hyperpolarizes the photoreceptor. Light will result in less release of glutamate. So an on bipolar cell has to accept that signal of less glutamate as light. Okay, so what it does is it has a inhibitory metabotropic glutamate receptor. And when glutamate is coming to the on cell, to the on bipolar cell, the glutamate actually inhibits the on bipolar cell. but glutamate is released in the dark. Okay, so the inhibition of the bipolar cell occurs, okay, because the system is dark. When you turn on the light, you reduce the glutamate. When you reduce the glutamate, you reduce the inhibition of the bipolar cell because the glutamate was inhibiting it through the metabotropic receptor, and that results in depolarization of the on bipolar cell. So because light results in a hyperpolarization, a negative sign, if you will, you have to put a negative sign in place to make the bipolar positive, to respond. So it responds to light with a positive response. In order to get that, it has to reverse the sign of the glutamate. And that's how it does it, through this receptor. On the other hand, the off system is a direct system, all right? So all you want to do is when the glutamate comes in, it excites this cell, this off bipolar cell, and therefore the ganglion cell knows that it's receiving more information from this off bipolar cell, meaning that it's dark, okay? That's the way it works. And once it hits the ganglion cell, it's transmitted with its off burst or on burst or whichever it is. Now, here we are. Here's our three figures again, the same three that we saw before. Ambient lighting, dim ambient lighting, a bright center, dim ambient lighting. So look what happens to the cone, right? It hyperpolarizes, all right? As a result of the hyperpolarization in the presence of light, it doesn't inhibit the on bipolar cell, which becomes more active, all right? But this hyperpolarization, if I said depolarization, I'm sorry, this hyperpolarization, all right, directly makes for a hyperpolarization of the bipolar cell, okay? And so in the on system, it goes from hyperpolarization of the photoreceptor, depolarization of the bipolar cell, and neuronal firing in the ganglion cell. If this is a off-center bipolar cell and ganglion cell pair, then the hyperpolarization of the photoreceptor results in a hyperpolarization of the off bipolar cell and a cessation of firing in the off ganglion cell. And so that's the way it works. And this one is just the opposite. It's the same logic but reversed. Okay? So, we've just been over that, and we don't need to go over it any further. All right. Here now is, no, we don't need to do it again. We've done it. All right. Let's talk about edge detection. So now you have this concept of on-center, off-surround. It's mediated by really the connection of the photoreceptor to the bipolar cell and the faithful interaction of bipolar cell with its own ganglion cell. And in the case of rods, the connection is via the amacrine cells. Now, here you go. So one pretty obvious, I think, the more obvious consequence of having on and off surrounds is that it improves edge detection. So now, this is obviously built for contrast, okay? Each receptive field has an on and an off region. The ganglion cells are most sensitive to luminance contrast. That's what I keep saying. A uniform level of luminance, whether dim or bright, makes no difference because the center and the surround are both receiving the information. They antagonize one another, and so you don't get a lot of output into the bipolar, from the ganglion cell. Is the bottom line, okay? So large fields stimulate them both, and you get very little. It's the small stimuli which are able to maximize the efficiency of the center surround, and that is what the nervous system is interested in. How many times, let me ask you a question, how many times has anybody looked, during this lecture, how many times has anybody looked at this spot right here? Okay, not counting Lakshmi, okay? None. Why? Why would you look at this? Who cares? Okay, it's there's nothing going on in it. Okay, if you want something to go on, somebody look at it. Put the French fries there, and then everybody will look at it, right? Okay, right? I mean, so you see, it's always going on. You just don't realize it. I mean, that's what's so beautiful about basic neuroscience is it explains your own behavior, and you go, oh, so that's why I have no choice but to not look at that. All right. This is the physiology of it, and this is just showing you if the light were only in the on center, only, mostly in the on center, mostly only in the off surround, falling off the receptive field, outside the receptive field, and you can see that you have different levels. Here, where it's half and half on, half off, you get nothing. When it's in, you get a big signal. When it's partly in, you get a little signal, okay? This is the light is stimulating both the on center and the off surround, okay? So, okay, this is a little bit obtuse in my mind, but roughly speaking, you could see, so here's light, here's dark, okay? If you have this on center cell mostly in the dark, you don't get a lot of signal, but you get, and what you get is negative anyway, because the only part that's being stimulated is the on surround. Okay. All right. Here you get a lot of signal because your on center is being stimulated nicely. So that's edge detection, and you can get a sense of that's the kind of signal that you could figure the central nervous system can easily process that kind of information. Okay, and much more than that. That's not hard. Then all we have to do is finish with light adaptation, and we've set the problem before. And so the question is, how do you do this? And the answer is the same way that you detect an edge. When you have a lot of luminance coming in, so I'll show you in the next slide, which is a great slide, but a little bit complicated. And again, we keep saying that the retina is not measuring luminance, it's measuring what's called luminance contrast. I sent you a URL link the other night. It was just sort of fun. I don't know that you're going to get anything out of it. Zhao Young probably will enjoy it. It was what I wanted you to get out of it, if you just start reading it, is this is done by engineers who are trying to figure out how to get people's attention for an ad. Okay? They want to catch your eye. And they hire it's a flashy colors. Yeah, but let's get into the detail of flashy colors. What is it about the flashy colors and so they get into the physiology of vision, which is, by the way, the original Helmholtz, and previous to Helmholtz was some French, were all about why the Italian carpets were so much more pleasant to look at than the French carpets. That was the beginning of color vision, of the understanding of color vision, because the king wanted the French carpets to outshine the Italian carpets, and he didn't understand as beautiful. They felt they had better workmen, but the Italian carpet, everybody loved the Italian carpets, and no one was buying French carpets. So the question was, what do we need to do? And they hired, I forget his name, French. He was a Frenchman who started it, and Helmholtz took over his work. And Helmholtz got to the point that he was measuring action potentials in optic nerves of animals as a function of color. Okay, but prior to that, this fellow did the color wheel was invented by this guy, and everything. And what it was the French had such beautiful gradations of dyeing. They were actually the better experts, and the Italians couldn't control the colors as well as the French did. So all they had were a few colors, and when they wove them together, they were bright and brilliant. And the French were beautiful, but what was happening was, because it was so graded, everybody was seeing gray. They weren't detecting the contrast. It's about luminance contrast, okay? And the French had no luminance contrast in their beautiful rugs. And that was the beginning of understanding of color vision, actually. It was totally commercial purpose, nationalistic commercial purpose. These are the 14, you have this in your chapter. These are the 14 orders of magnitude of luminance. You go everything from pitch black to looking at the sun at the wrong moment during an eclipse. Okay, so here you go. This is a great slide, and this really contains the bulk of the information. We are looking here at about 6 orders of magnitude of luminance. And that's here, okay? And each one of these corresponds to a different curve. Each curve is a function of the discharge rate as a function of luminance. And what you need to see is that each of these curves goes from 0 to 300 over 1 order of magnitude. So to get to see 6 orders of magnitude, you have to keep moving this curve. Okay? And so what happens is that in the dark, this is one receptive field. Okay? In this dark, we're not moving the electrode. This is only one receptive field on the eye. Okay? And they're doing a test flash. Okay? And they're not moving it. They just keep tapping the same spot on the retina. Okay? And what they're changing is the ambient lighting. Okay? As a function of ambient lighting, so when you're in dim ambient lighting, that receptive field only responds to 1 orders of magnitude, but the order of magnitude is from 10 to the minus 4th to 10 to the minus 3rd. Take that same receptive field and increase the ambient lighting, and its 1 order of magnitude response is shifted by an order of magnitude approximately. And so what you're really recording is what intensity of test stimulus do you need in order to generate a firing rate of 10 or 200 or 300. So what you're seeing is that the system is very, very sensitive in low ambient lighting and very insensitive at higher ambient lighting. But so in other words, the retina keeps adjusting itself so that it uses this 1 to 2 orders of this 0 to 300 firing rate. It doesn't want it spread out over 14 orders of magnitude. It wants it concentrated in about 1 to 2 orders of magnitude of luminance. And everything that's below that and everything that's above that is going to be uniformly lit, and it doesn't want to know. Okay? And that's what's going on. Now, when you change, so let's say that we're fixing the back of a TV, all right? And we want to see if the plug is okay. And the first time that we turn the TV so it's to the window, and we get the most light on it that we can. And then we don't see the problem there, but there's this little panel area that is hidden from the window, and we can't turn the TV anymore. So now we have to look in here. So, of course, you could reach for your iPhone and put the flashlight on, okay? But if you don't do that, and sometimes you don't have your iPhone there, you just wait a second, and pretty soon what was uniformly black suddenly has detail. And that's what's happened, right? Your retina has those visual fields have moved from this kind of lighting to this kind of lighting, and so that they maintain that luminance contrast of only 300 hertz into the range of interest. That's basically it. So you're scaling the ganglion cell response to light as a function of ambient luminance. I think we've said it. We don't need any more slides. The surround mechanism enables us. The horizontal cell is the key here. This is the one piece that I want to talk about now. So it's the horizontal cell system that accomplishes this, because the horizontal cells receive synaptic input from the photoreceptor. What the horizontal cells do is they make a syncytium. Remember gap junctions? Remember we talked about gap junctions or electrical synapses? Okay? Horizontal cells in the retina are all communicating with one another. They're almost like a astrocyte in a certain way. Okay? So that whole horizontal cell layer is a syncytium. When you try to alter it, okay, you're altering the whole thing. It's spreading it out throughout large areas of retina. This will be good for dark vision. This will be good for adaptation, okay? And so it's the horizontal cells that do that because they're all interconnected via gap junctions. It's, quite an interesting mechanism, okay? And that's basically what I'm saying in here. And then, of course, okay, the horizontal cells, their action, their output, is a presynaptic output onto the photoreceptor cell. So they say to the photoreceptor cell, slow down that glutamate release, okay? In order for me to see what's going on here, I need you to slow down a little bit as a basal state. And so the horizontal cell syncytium controls the basal sensitivity of the photoreceptor by a presynaptic inhibition, okay? And then you have the synapses onto the bipolar cell. I mean, I think that's basically it. The horizontal cells do that. The presynaptic inhibition is via GABA, and the result is that the whole system is controlled. And this summary slide really does the whole thing. Here are your horizontal cells. I'm not going to go over it with you. You can take the time to go over it. Here's an Oncenter cell. And if you walk through this, you'll see that it makes perfect sense. Remember, as you try to go through this diagram, that T is time, okay? And this is a movie, if you will, of what's happening. And so as you look at T0, don't think of it spatially, think of it as temporally, okay? All right, that's it. It was a very interesting chapter. I thought it was a very good book chapter. All right, and that's it.
Thank you.
Goodbye, everyone.
Stop.
No, get it.
Today is 26, right?
Where do you have on the H drive, where do you have the lectures? All resident
Do we have
lectures.
the folder for the lecture?
Textbook, educational materials. Neurophysiology, okay, no, it's actually not on here.
Yeah.
I'm just gonna put it in here.
Yeah, we've been putting it on that website, so we haven't really been seeing it on.
I see, okay. Well, how do you want me to?
No, we can.
You can
we
create one right now.
So I'm just gonna put it here and you can move it where you want later.
Okay.
It's too big for me to send you. It's
Right.
25 gigabytes or something like that. It's a massive file.